Hello, my dear students. I believe you are doing very fine whilst you are home in this era of COVID-19. I also trust that you are studying seriously. I want to urge you to continue studying whilst you are home so things are normal for us to meet face to face at school. My name is St.Monica, your general chemistry tutor. I'll be handling this course with Mr. Charles Kwame Bando, and today we're looking at Unit 2 of General Chemistry with course code EBS132, and the topic is formation of ionic and covalent compounds. Now, the performance indicators that we expect you to exhibit at the end of going through this section is that you should be able to explain the term compound and give examples. You should also be able to explain ionic and covalent bonding with diagrams. And finally, you should be able to distinguish between ionic and covalent compounds on the basis of their properties. First, we are looking at compounds. Most of the time when students are asked to explain or define compounds, there is a common phenomenon that you see, especially when you are marking scripts of students. This runs through right from BEC, SSC, and even sometimes at the College of Education. Now, when we say a compound is a substance containing two or more different elements, chemically combined in a definite proportion by mass. Most of the time you see students writing a compound is the chemical combination of two or more elements. This definition is not appropriate, because when you are asked to give an example of a compound, you will not give a process. You will give a specific substance, for instance water, carbon dioxide. So that's a compound. So in this sense, if you are asked what a compound is, the underlying factor is that it is a substance, and this substance contains two or more elements that have been combined chemically by a definite proportion. Like I mentioned earlier on, when you are asked to give examples of compound, there are so many of them. You can talk about water, and that is the structure of water. You know, it is made up of two hydrogen atoms and then one atom of oxygen. So we have a single bond of the hydrogen to the oxygen, and then another single bond here from the hydrogen to the oxygen. Now, sodium chloride is also another example, and this is formed between the element sodium and then chlorine, and that's also the structure of sodium chloride. Many examples are there. You can talk about methane, you can talk about ammonia, you can talk about silica, and so on and so forth. And so there are so many of them. Now, carbon dioxide, like I mentioned earlier on, is what you also see there, and that is the structure of carbon dioxide. Now, this one is supposed to be a double covalent bond from the carbon to the oxygen here, and then another double bond here from the carbon here to also the oxygen. So together, that is what makes up the structure of carbon dioxide. And this is a double covalent bond. This is a single covalent bond. All these are examples of compounds. Going forward, we will meet so many examples. Now, this compound that we are talking about as a concept can be grouped under some headings. We can have some compounds that are solid in nature, some also liquid, and some also being gas. When you take examples of compounds that are solid, we can talk about common salts, that is sodium chloride. We can also talk about saltpeter. We can talk about marble. We can talk about copper 2 sulfate. We can also mention sugar, clay, and then sand. All these are examples of compounds that are solid. Now, when you take examples of compounds that are liquid, we can also mention water, we can mention sulfuric acid, we can mention ethanol. and then many more. Gases, we can also talk about carbon dioxide, we can talk about ammonia, and then we can also mention methane. And examination, you can be asked to give examples of compounds that are liquid and then talk about their constituent elements. And when it happens like that, we don't expect you to be mentioning any of the examples here. Neither do we also expect you to be mentioning any of the examples here. We solely expect you to talk about examples of compounds that are liquid, like water, like sulfuric acid, like ethanol, and so on and so forth. So further, we're looking at further examples of compounds with their constituent elements. Like I mentioned earlier on, you can be given even some of their compounds, and then you'll be asked to provide their elements as well. So when you take water, you see we have oxygen and then we have hydrogen. Earlier on, when you saw the structure, you realize that we have 2 atoms of hydrogen and then 1 of oxygen making up water. Then if it comes to sugar and glucose, they are all monosaccharide, and then we have oxygen, we have hydrogen, we have carbon. These are the elements that constitute both glucose and then sugar. Then common salt, sodium chloride. As we mentioned earlier on, we have the elements sodium and then chlorine. When it comes to saltpeter, potassium is there, nitrogen is also there, and then oxygen. Then marble, that is calcium carbonate. The elements calcium, oxygen, and carbon combine to form marble. Now when it comes to copper 2 sulfate, we have copper itself there, sulfur is also there, and then oxygen. Then ethanol, alcohol in principle, also contains carbon, hydrogen, and then oxygen. Now when it comes to ammonia, then we also have nitrogen and hydrogen. Then sand will give us silicon and oxygen. Then clay, you can talk about aluminium, you can talk about silicon, oxygen, and hydrogen. And finally, when you mention methane as an example of a compound that is a gas, you can also talk about carbon and hydrogen, which make up methane. The formula for methane is CH4. So here we are talking about 1 atom of carbon and then 4 atoms of hydrogen combining to give us that. Now next, we want to look at what a chemical bond is. In our lecture lights, you also realize that as students, when we are in school, we also engage in some form of bond. So literally, we can talk about a bond as a form of an agreement. For example, if you are at a dormitory and then getting to the tail end of the semester, you realize that you left with only Gary, and then you don't have anything. Meanwhile, you want to do soakings. You cannot contact a friend and find out if that person will be able to provide you with milk, others providing you with sugar, and you put all of them together. Before you realize, you have your soakings and then you are going. When that happens, there is a kind of agreement that has been formed between all of you, and then at the end, all of you will get something to eat. In the same vein, these atoms that we are mentioning, they also go into some form of agreement. They go into some form of bonding. And the essence of their agreement or bonding that they make is to ensure that they achieve stability. So realize that there are some elements they are already stable. For example, when you pick the group 8 elements, we can talk about helium, we can talk about neon, we can talk about argon. These are already stable. So hardly will you find any of these elements that I have mentioned in any compound. Hardly will you find them in any compound because they are already stable. So those who go into chemical bonding are those that are unstable in nature, and then for that matter they want to achieve stability. So then a chemical bond is a force, and that force holds atoms, it holds ions as well as molecules together. That force that holds atoms, ions or molecules together is what is referred to as a chemical bond. Like I've already echoed, bond formation involves gain, loss or sharing of outer shell electrons of atoms. And so when these atoms are going into that kind of bonding, some of them they gain electrons, others also lose electrons, and for others they share electrons. And so these electrons of the atoms are shared, are lost, and again in the formation of chemical bond. Bonds are formed so that each atom gains stable electronic configuration that is similar to that of a noble or inert gases. When we talk of the inert gases, formerly group 8 and now group 18 elements, I have already said that they are already stable. For example, the neon, the argon, the helium. And so atoms that go into bonding would also want to ensure that they are stable in nature, just like that of these noble or inert gases. What then is a noble gas? I have already echoed about it. A noble gas has a fully filled outermost shell containing 2 or 8 electrons. For example, when you pick helium, there are 2 electrons that are there. The atomic number is 2. And it has only the first shell, and the first shell takes a maximum of 2 electrons. So it means that it has a complete electrons that are needed to be accommodated on that shell, and that makes it stable. When you pick neon, the atomic number is 10. And so when you are drawing the electronic configuration, you talk about 2 on the first shell, and the next shell can accommodate a maximum of 8 for the first 20 elements, of which neon is part of it. And so that's also stable. Then when you pick argon, the atomic number is 18. It means that there are 18 electrons there. And so when you are drawing the electronic configuration, the K shell takes a maximum 2. The next one, that is the L, can accommodate 8. And then the subsequent one, M, also takes a maximum of 8. And so these are fully filled outermost shell of their atoms, and because of that they are stable. Now, how do atoms achieve stability? Now, metal atoms that have 1, 2 or 3 electrons in their outermost shell will always donate or lose these electrons to become positively charged ions or cation. For example, when you pick the group 1 elements, we have lithium there, we have sodium there, we have potassium. When you pick lithium, it has atomic number 3. It means that there are 3 electrons in there. When you are drawing the electronic configuration for lithium, the first shell, which is the K shell, will take 2. And then the last shell will pick 1. Then when you pick magnesium, that is also 12, atomic number 12. It means that when you draw the electronic configuration, the first shell will take 2, the next one 8, making 10. Then the last one 2, so it has 2 electrons on its outermost shell. When you pick aluminium, aluminium is also with atomic number 13. It tells you that its configuration is 2, 8, 3, making 13. So the last shell takes a maximum of 3 electrons. So these elements that I have mentioned as an examples, you realize the lithium will have 1 on its last shell. When you pick sodium, atomic number 11, that is also 2, 8, 1. It also has 1. When you pick potassium, atomic number 19, its configuration will be 2, 8, 8, 1. So in the quest to achieve stability, they will give out all these 1, 1, 1, 1, 1. That is the group 1 elements out, so that it will be left with the shell that has a maximum of 8 on its outermost shell. When the electrons are gone, the shells are also gone. Then they can achieve stability. When you pick the group 2, like the beryllium, which is atomic number 4, and then its configuration is 2 on the K shell, 2 on the next shell, it will give out the 2, so that the first shell will maintain the 2, that will make it stable. Because that next shell, that also has the second 2, you realize that it's supposed to have a maximum of 8 electrons. So to achieve stability, it either needs 6 electrons to be added to the 2 to make it 8 so that it can be stable, or it will give out the 2. But in principle, no atom will actually give you 6 when it has it on its outermost shell, because having 6 means that it can easily get the 2. And so then beryllium will be left with no option than to give out the 2 to become positively charged iron, and that will make it stable. Now when you pick aluminium, like I mentioned earlier on, it also goes through the same principles. So realize that atoms with 1, 2 or 3 electrons in their outermost shell will always donate or lose these electrons to become positively charged ions or cations. When you pick non-metal atoms, those that have 5, 6 or 7 electrons in their valence or last shell will always accept or gain electrons. So for instance, when we talk about a non-metal with 5 electrons, we can mention phosphorus. Phosphorus has atomic number 15 and its configuration is 2, 8, 5. So having 5 at its last shell, that shell is supposed to have a maximum of 8 for it to be stable. So then easily it can obtain 3 in addition to the 5 to make up 8, so that it will make it stable. Now talking about non-metal with 6, we can mention sulfur. Oxygen is also another example. When you pick sulfur, for instance, it has atomic number 16, and so its configuration is 2, 8, 6. It means that that 6 on the large shell is not making it stable because it needs 8. And having 6, it means that I can easily get 2 in addition to the 6 to make up 8. And so then it will always receive the 2. Now those that have 7 electrons, we can mention fluorine, we can also mention chlorine. Fluorine has atomic number 9, and so the first shell takes 2, and then the last shell takes 7. And if it has 7, it can easily get 1 to be added to the 7 to make up 8. And so it always receives. Chlorine is also atomic number 17, and then it has 17 electrons. And so its configuration is also 2, 8, 7. And that 7 needs 1 to be added to it to make up 8 so that it will be stable. So atoms of elements with 5, 6 or 7 electrons in their valence or last shell will always accept or gain electrons to be added to it to become 8, so that they become negatively charged ions, which are called anions. 2 non-metallic elements with 4 to 7 outer electrons may also share electrons with each other. For example, when you take carbon with atomic number 6, you realize that first shell takes 2, the last one is 4, so it has 4 electrons. Normally it goes into covalent bonding. Having 4 means that it can either lose the 4 or gain 4. But in principle, it's very difficult to get the 4. So normally what it does is that it goes into covalent bonding, which is sharing. So that's about that. Silicon is also another example that we can talk about here. And so 2 non-metallic elements with 4 to 7 outer electrons may share electrons with each other. So you see carbon sharing electrons with oxygen to form carbon dioxide. And then next one, let's look at valency. This concept valency, sometimes students find difficult to internalize, but it's very, very easy. If you really understand the concept well, you wouldn't need to memorize anything. So what then is this valency that we are talking about? The valency of an element is the number of electrons. Take note, the number of electrons that are either lost or gained by an element in a chemical combination. I am repeating it. The number of electrons that are lost or gained. The number of electrons that are lost or gained by an element in a chemical combination. So for example, when we pick sodium and chlorine, they combine to give us sodium chloride. Now sodium has atomic number 11. So realize that its configuration is 2, 8, 1. It has 1 electron on its last shell. Now chlorine has atomic number 17. And so its configuration is 2, 8, 7. Its last shell has 7 electrons. So in the formation of a chemical bond between sodium and chlorine to form sodium chloride, you realize that sodium will give out that 1 electron on its last shell to the chlorine, for the chlorine to have 8. So that 1 electron that it's giving, that is what is called its valency. So when you go back, I said it is the number of electrons that is lost or it is gained. So in this case, if sodium loses 1 electron, it has a valency of 1. Now the chlorine in that chemical combination accepts that 1 electron, and that 1 electron that is accepted is also its valency. And so the valency of chlorine is 1. So realize that if you understand it in this perspective, then easily, when we ask you what is the valency of sulfur, quickly you get to know that sulfur is with atomic number 16, and that is why you are supposed to then the first 20 elements in the order in which they occur, so that when we mention sulfur, quickly you get to know that it's with atomic number 16. And that 16 has a configuration of 286, means that it will need 2 to be added to it to make up 8 so that it will be stable. That 2 that it is gaining, it's 8 valency. And so the valency of sulfur is 2. When you pick oxygen, atomic number 8, the configuration is also 26. You also realize that it will need 2 to be added to the 6. And that 2 it is gaining, it's 8 valency. So we ask you the valency of sulfur, straight away you tell us it is 2. Take note, students get confused with valency and charges. When you talk of valency, we are not talking about the charges. It is just the number of the electrons that are either lost or gained by the elements when it is chemically combining with another one. So if I ask you what is the valency of aluminium, straight you get to know that aluminium is with atomic number 13, meaning that in its neutral state it has 13 electrons. The configuration is 2, 8, 3. So for it to be stable, or when it is combining, it has to give out the 3 electrons. For example, if aluminium is combining with chlorine to form aluminium chloride, it will give out all the 3 electrons. So that 3 electrons on its large shell that it is giving out for it to be stable in the chemical bond is 8 valency. And so the valency of aluminium is 3. The valency of boron is also 3. So when we mention magnesium, straight away you get to know that it's 2, because magnesium has atomic number 12 electrons. Configuration is 282. It will give out that 2, and that 2 is giving out its valency. So in principle, we're saying that the valency is the number of electrons lost or gained by an element in a chemical combination. So this is a table of some elements, their symbols, their charges, as well as their valency. So if you understand the concept well, as soon as we mention lithium, straight away you tell us that the valency is 1, because you get to know that lithium has atomic number 3, and then first shell takes 2 in its configuration, and the last one is 1, and it is that 1 that it will give out, and that 1 is 8 valency. Same applies to sodium with atomic number 11, and so 281, that 1 will be given out, and so the 1 is 8 valency. Potassium, also atomic number 19, they are all group 1 elements, so 2881, so that 1 will be given out as 8 valency. I mentioned magnesium, and so 12, straight away you get to know that is 282, and so that 2 on its large shell will be given out, and that is 8 valency. Calcium is also in group 2, that is alkali earth metals, and that is also having a valency of 2. Boron, like I mentioned, and aluminium, they are having 3 as their valency, because boron has atomic number 5 electrons. So configuration is 2, 3. So the last shell will have 3, and these 3 electrons will be given out, and that is 8 valency. Aluminium 13 will give you 283, and the 3 will be given out. Silicon, that is 4, because it is 14, and that is 284, and that 4 that it will either give out or accept is its valency. Oxygen, of course, is atomic number 8, like I mentioned, and 2, 6, so it will need 2 to be added to it. So the 2 it's gaining, it's 8 valency. Sulfur is 16, and that is giving you also 2, because it's 286, and that will need 2 to make up the 8 on the last shell. Finally, chlorine is 1, as I have explained earlier on. So that's about the concept of valency. I believe that you have understood it well, and you can give examples of yourself and then mention their valencies. Now moving on to formation of ions. Take note of the word ions, I-O-N-S. This is different from I-R-O-N, and so that is an ion. When we talk of an ion, it is simply an electrically charged particle or atom. When we say an atom is electrically charged, it means that it has either lost an electron or gained an electron. And so when it loses an electron, it becomes electrically charged particle. When it gains an electron, it also becomes electrically charged particle. So an ion is an electrically charged particle or electrically charged atom. How are ions formed? They are formed when atoms lose or gain electrons in order to attain stability of the noble gases. They are formed when atoms lose or gain electrons in order to attain stability of the noble gases. These ions that we're talking about, there are types of them. The very first one is what we refer to as cations. So when we talk of cation, what are we referring to? These are formed when atoms or group of atoms loses one or more electrons from their outermost shell. When an atom or group of atoms loses one or more electrons from its outermost shell. So anytime there is a loss of an electron, it leads to the formation of a cation. So for example, the same magnesium that I used earlier on, if it loses two of its outermost electrons, I mentioned magnesium is 12, so its configuration is 2, 8, 2. So that 2 that is on its last shell, when it loses it, it then becomes 2+, and that makes it a cation. So anytime an atom loses, or a group of atoms loses an electron, it becomes a cation. So a metal atom with 1, 2, 3 electrons in their outermost shell readily loses their outermost electrons, and then they form positive ion, which is called a cation. The next type of ion is anion, and here we are talking about negative ions. So when you hear anions, negativity must come into your mind. They are negative ions. They are the ones you see a negative sign on the extreme right top of it, and cations are the ones you see a positive sign there. So an anion is a negatively charged ion formed when an atom gains one or more electrons into its outermost shell. A negatively charged ion formed when an atom gains one or more electrons in its outermost shell. So for example, when you go back to oxygen, oxygen is with atomic number 8, and then its configuration is 2, 6. So for it to be stable, or when it is going into a chemical bond with any other atom, that oxygen will have to gain 2 electrons to it to make it stable. Now when it gains the 2 electrons, it becomes 2-, and that is an anion. So once it gains, you see a negative sign. When the atom loses, you rather see a positive sign. And so anions are formed when atoms gain electrons to themselves, especially the last shell. The number of negative charges an ion carries is always equal to the number of electrons that is gained. So for example, when chlorine gains 1 electron, you just see a negative charge there. That one, we don't put the 1 there. The negative charge just represents that 1 electron that it has gained. But then when it gains 2, 3, 4, then respectively you will see 2 in front of the negative charge, meaning that it has gained 2 electrons. You see 3, meaning that it has gained 3. When it gains 4, 4 is written in front of the negative charge on top right of the atom. And so for example, sodium atom easily loses an electron to be more stable because it has only 1 electron in its outermost shell. This is for the cation that we mentioned. Now when sodium donates 1 electron in its valence shell, the number of electrons will be 10 instead of 11. I have explained this already. And this is a pictorial diagram that explains that. If you look at the diagram that you see on the board, you realize that this is sodium atom, a neutral sodium atom. Its atomic number is 11. And if you are drawing the electronic configuration, which you have already learned, you will have sodium first shell picking up 2 electrons, that is the K shell. The next one, according to the rules, will take 8 electrons, 2, 4, 6, 8. Then that will make up 10. So the last shell has this one. And so in the formation of an ion, this sodium atom will lose this 1 electron. And when it loses that 1 electron, this electron and that shell will go off. So it will be left with 1, 2 shells. These are the ones you see there, with the first one closer to the nucleus being 2 electrons, and then the electrons on the next shell also making up 8. And so that is how sodium ion is formed. Now when it comes to chlorine, you also realize that chlorine, like I said, has atomic number 17. So its configuration is 287. The first shell takes 2 electrons, 1, 2, as you see there. And take note that always when you are using diagrams, your nucleus must feature. If the nucleus is not there, it doesn't represent an atom, and whatever diagram that you draw will be incorrect. And so the first shell takes 2 out of the 17, then the next one 8, making 10, so 2, 4, 6, 8. Then the last shell will take 7, so 2, 4, 6, 7. Now for it to become an ion, these 7 electrons on this shell must be 8. And so then there is an additional electron that is added to this shell to make up 8, and that is what you see there. So when this electron is added, then the number of electrons on this outermost shell or valence shell become 8. And that is what you see there, 2, 4, 6, and then 8, as you see there. And so now that it is 8, because it has gained 1 electron, it then becomes chlorine minus. And so that is how chlorine also forms an ion. So for the purposes of explanation further, chlorine has an atomic number of 17. The electronic configuration of chlorine is 287, and then chlorine is also in group 7 and tends to gain an electron to be stable, and that is what you see diagrammatically. I mentioned group 7 and I was laughing. That was the old way of grouping elements on the periodic table. Now it is in group 17, but the two are used concurrently, and that's why I was laughing. Now, ion formation patterns. How are the patterns with which ions are formed? In general, atoms form ions according to the patterns that we are going to talk about. Metals in group 1. Group 1 are called alkaline metals. They have only 1 electron in their valence shell. We have mentioned them. Example, lithium. Example, sodium. Example, potassium. They are all in group 1 and they are called alkaline metals. They always have to possess 1 electron in their valence shell when you draw the electronic configuration. Then they can give up this 1 electron and become positively charged atoms. Now group 2 elements will always give up the 2 electrons to become 2 plus, and group 3 will give up 3 electrons to become 3 plus. So example of group 2, as we have mentioned, they are called alkaline earth metals. Beryllium is there, as well as magnesium, as well as calcium. All these are in group 2, and they will all give out 2 electrons to become positively charged, having 2 in front of the positive. Example of group 3, they are the boron group. So boron and then aluminium are there. Boron with atomic number 5, 2 on the first shell, 3 on the last shell. When you're drawing the configuration, we'll always give out a 3 for it to be stable. Aluminium 13. We have talked about this already, so that is just the pattern within which the ions are formed. Non-metals in group 17 need just 1 electron to complete their valence shell. For example, chlorine, for example, fluorine. They can gain 1 electron and become group 16 elements, gaining 2 electrons also to become 2 negative. And group 15 elements gaining 3 electrons to become 3 negative. I want to go over this. We are saying that they can gain 1 electron to become negatively charged. That is group 17 elements. When we pick group 16 elements, that is the sulfur, the oxygen, they can gain 2 electrons to become 2 negative. And group 15, like for example, phosphorus element, will gain 3 electrons to become 3 negative. All the remaining metals elements produce at least 1 ion with a charge of a positive sign. Now some elements can form ions with 2 or more different charges. For example, iron. Ion can form both ion with +2, that is ion 2, and then ion with +3. So this one, they have variable oxidation state as well. Now copper is also there. We have copper 1 and then we have copper 2. So these elements can form ions with two different charges. So now we are moving on to ionic compounds. And like I was saying, I want to crave your indulgence to be particularly attentive here. Most of the time when it comes to ionic bonds, the bonding, covalent bonding, students give some form of laissez kind of an attitude towards it. If you take your time and you follow it closely, you really understand it better. And so just give the maximum attention that you can to this and follow it closely with your mind, and then I believe that you'll be able to get the diagrams very well. What is an ionic compound? Simply, an ionic compound is a compound that is formed by ionic bonding. A compound that is formed by ionic bonding is an ionic compound. It's as simple as that. Now let's consider these two scenarios. One, look at the image of the two poppies that you see there. This is one and that is another one. You realize that one of the poppies has a bone. We are referring to this particular one. Now these poppies that we see represents atoms. So this is one atom and this one is one atom. This is just an icebreaker to lead you into a better understanding of this ionic bonding that we are going to talk about. Now the bone that you see in the mouth of this poppy represents an electron. So we are referring to this as an electron. Now the poppies are both neutral. So this is a neutral atom. This is also a neutral atom. Then if one of the poppy becomes a thief and decides to steal the bone from the other one, so you are referring to this as a thief, stealing the bone from this one, what will happen? You realize that the poppy thief now will be in possession of the bone. Then the poppy that does not have the bone, now it's been taken from this, that's lost its electron and it's now positively charged, will then follow the poppy which has a negative charge, which is this one, because it has gained the electron. And this one has lost it, so it has become a positively charged. So realize that this one will follow this one. That is the one with positive charge will follow the one with negative charge. Then that negative charge will follow around, and when the two come close together like this, they form what is referred to as a poppy pair. This poppy pair is what is an ionic compound. So what can you draw from this scenario? It tells you that in the formation of an ionic compound, there is always a movement of an electron from one atom to another atom. And when one donates it, it becomes a positive charge. When one accepts it, it becomes a negative charge. And from the first law of thermodynamics, as we know, like poles repel, like poles attract. So naturally, they attract each other and then they form the bond, and they will all be stable in the bond, and that is how it is. So in the concepts or context of chemistry, when we talk of an ionic bond, which is also an electrovalent bond, it is an electrostatic force of attraction, between a positively charged ion, which is called a cation, and a negatively charged ion, which is called an anion. So electrostatic force is a force of attraction between oppositely charged particles. And formation of ionic or electrovalent compounds, how are they formed? Ionic compounds are compounds formed from ionic bonds, like we have echoed earlier on. There are so many examples of ionic compounds. We can talk about sodium chloride, we can talk about lithium fluoride, we can mention calcium oxide, aluminium chloride, aluminium oxide, magnesium chloride, magnesium oxide, All these are examples of ionic compounds. And in examination, you can be asked to use diagrams to show how the nature of bond occurs in any of these examples that I have mentioned. So first, we are going to learn how to use diagrams to explain the formation of sodium chloride. First, we are looking at sodium and chlorine ions. So if you consider the ions formed from sodium chloride, we will have sodium ion, that is Na plus, combining with chlorine ion, that is Cl minus. And the ionic equation will be sodium plus chlorine minus, and it will give us a neutral sodium chloride. Sodium chloride is an ionic compound. This is because it is formed from the combination of two oppositely charged ions. Here we are talking about sodium plus and chlorine minus. So if you look at the diagram that you see there, this is sodium, atomic number 11. So its configuration, normally when we are drawing the diagram, it is the electronic configuration that we use to draw. First, you need to draw your nucleus, and the nucleus, you can draw this and write the sodium in it, or you can put the proton and the neutron in it to form the nucleus. Then you draw the first shell. This is from drawing all the shells before you put the electrons on it. You are likely to encounter a situation where your shells may be more than the electrons, and when it happens like that, it will make your diagram wrong. So as and when you draw the shell, then you put the electrons on it. So the first shell takes 2 electrons, as you see, then the next one 8, then the last one 1. That is sodium. Then when you come down, you see chlorine. Chlorine is also with atomic number 17. So you realize that after the nucleus, the first shell takes 2, the next one 8, and the last one 1, 2, 3, 4, 5, 6, 7. 7 electrons. Now what happens is that in the formation of sodium chloride, this sodium is going to give this last electron on its valence shell, which prevents it from achieving stability to the chlorine. So that the chlorine having 7 on its outermost shell will now gain 8. And so when it happens like that, when the sodium gives out 8,1, it will be left with this shell that has 8 electrons as its valence shell. That will make it stable. And then the chlorine will also have 8, and the 2 of them will be stable, and then they form the compound. So as you see in the diagram, this is sodium. Now look at what is happening. You realize that that electron that is found on its last shell, it is giving that to the chlorine. And once it does that, the chlorine then gets its 8, and then the 2 become stable. And so that is how the formation of sodium chloride is done. So when that happens, the natural attraction occurs between sodium and chlorine, and then they form the sodium chloride. Now this is the crystal lattice structure of sodium chloride, how they are. You see, we have the pink color, and then we have this other color representing the sodium and the chlorine. So the anion is the chlorine, which is with this, and then the cation it's with this color, and that is the sodium. So in the formation of ionic bond, as you see there, that is what happens. Sodium has last electron, and then it gives that electron to the chlorine. And once it gives that electron to the chlorine then becomes 8. Sodium also will then be left with 8 electrons on its last shell. And when it happens like that, all of them become stable, and then the natural attraction occurs between them, and they form the compound sodium chloride. Formation of magnesium chloride. In fact, we cannot draw all the diagrams here. And so once you understand the concept, the examples that I mentioned, the calcium oxide, you can try that on your own. The aluminium chloride, the magnesium chloride, and the aluminium oxide. That of aluminium oxide, it's interesting. Try it and you see. You realize that aluminium has atomic number 13. And so when it is giving the 3 electrons on its last shell to the oxygen, oxygen has 6 on its last shell because it is 8. First one takes 2. It can take only 2. So when that oxygen takes the 2, then it will be left with 1 of the aluminium electron. And so then what happens is that oxygen then brings another oxygen atom that also comes to take 1. Meanwhile, that one also has 6 electrons, it needs 2. Then aluminium will bring another atom which is also having 13. So the last one is also 3. And so the 3 electrons, one will be added to the second atom of chlorine. Then it will be left with 2 of the second of the aluminium. And so then oxygen also brings another one. And when it brings that one, it also has 6. Then it come and take the last 2 of that of the aluminium. Then aluminium oxide is 4. And so it's very interesting. I urge you to try it and then see. Next, we are looking at formation of magnesium chloride. You know, magnesium chloride, the formula is MgCl2. We are not going to explain why when you write MgCl, you have to bring 2 as a subscript to the chlorine. Other than that, the formula that you write will be wrong. So pay attention and then listen attentively. So magnesium has atomic number 12. Its electronic configuration is 282. Now let's look at the diagram. This is magnesium. So after bringing the nucleus, the first shell takes 2. The next one 2, 4, 6, 8. The next one 2, making 12. And so for magnesium to become ion, that is magnesium 2+, it has to give out these 2 electrons to the chlorine. And so in the formation of an ion with magnesium, when this one gives out the 2, that is 2 electrons added to this one, it then becomes magnesium 2+. That is when it loses the 2 electrons. So if we want to balance it, this side we have 2, and then we have 8, and then we have 2. When you come to this side, the 2 electrons on the atom shell has already been given out. So it is left with just the 2 shells. First one picking 2, the next one picking 8. Now if you want to balance it, then we have to add 2 electrons to 8, so that it will be just like it is here, because as it is, this magnesium 2+ means that the electrons are 10, and then here the electrons are 12. So to make it balance, you add 2 electrons here to this one, so that it will be 2, 8 plus 2 electrons making up 10, 10. Then we can say that the ion equation is balanced. Now let's look at that of chlorine with atomic number 17. You also realize that its electronic configuration is 287. Now watch this. This is chlorine, 287. So again, 2 on the first shell after the nucleus, the next one 8, and the next one 7. 2, 4, 6, 7. Now when chlorine accepts an electron and it becomes chlorine minus, the last shell will have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then you realize that the configuration will be 288. Now if you want to write a balanced ionic equation for it, you realize that you have 8 electrons on its last shell here, but here there are 7. So to make it balanced, you also add 1 electron to this side, so that the electrons here as it stands is now 18, and then this one is also 18. So that is how ions are formed for magnesium and the chlorine. Now these ions then combine to give the diagram that we see there. So we have magnesium 2+, meaning that it has lost 2 electrons from its last shell and it's left with this one, combining with chlorine, which has also gained 1. Now take note here. You realize that in the formation of the bond, I said magnesium has 2 electrons come back here in its last shell. Now these 2 electrons will have to be given to the chlorine. But you realize chlorine atom has 17 electrons. The last shell is 7. It cannot take the 2 electrons from the magnesium. And so what it does is that one chlorine atom will just take 1 electron from the magnesium. Then it brings another chlorine atom, which will come and also take 1 electron from the magnesium. So in principle, in the formation of magnesium chloride, we need 2 atoms of the chlorine combining with just 1 of the magnesium. And that is why when you are writing the formula, you write MgCl2. So if you don't bring that subscript 2 there, and you just write MgCl, then you are telling us that that one chlorine atom will take all the 2 electrons from the outermost shell of the magnesium, which is not possible. And so always we need 2 atoms of chlorine. Each one has 7 electrons on its large shell, so each of them will pick one electron from the large shell of the magnesium, and that is why the formula is MgCl2. So you realize that if you are drawing aluminium chloride, which I will urge you to try, if you are even drawing magnesium aluminium chloride, it follows the same principle, just like the magnesium chloride. You see the aluminium will have 3 electrons on its large shell. Chlorine, one atom has 7 electrons on its large shell. It can only take one of the 3 from the aluminium. And so what happens is that chlorine brings 2 additional atoms, all needing 1, so each of them will pick 1 from the aluminium. That is why the formula is AlCl3, meaning that the subscript 3 will tell you that you need 3 atoms of chlorine combining with just 1 atom of aluminium to form aluminium chloride. So you try that one. Try all the other examples that I mentioned. Lithium fluoride, talking about calcium oxide, talking about magnesium oxide, and so on and so forth. Let me explain that of magnesium oxide. You realize that the formula for magnesium oxide is MgO. Now it means that in the formation of magnesium oxide, we need 1 atom of magnesium and 1 of oxygen. Now magnesium has atomic number 12, and so the electronic configuration 282. That 2 will have to be given to the oxygen. Now this oxygen has atomic number 8, and so its large shell, there are 6 electrons there. So it means that it needs 2. So in the formation of magnesium oxide, the magnesium atom can take all the 2 electrons from the oxygen atom can take all the 2 electrons from the magnesium, and that is why it is just MgO. But in the case of the magnesium chloride, 1 chlorine atom cannot take all the 2 electrons from the magnesium, and so then you realize that there should be 2 chlorine atoms, each one picking 1 from the magnesium, and so that is how it is formed. Now we're going to writing chemical formula for ionic compounds. Now the total negative charge must be balanced by the total positive charge so that the compound carries no net charge. In other words, we are saying that the compound is supposed to be neutral. So when writing chemical formula for, let's say, ionic compounds, you must ensure that at the end of it all, the formula that is written is neutral. So example, sodium chloride. Sodium ion plus chlorine ion will give you sodium chloride. So at the end, the positive and then the negative cancels out, and then it gives you sodium chloride. Now calcium chloride is Ca2 plus Cl minus, but 2 atoms of it. This is just like magnesium chloride. So at the end, we have calcium, 1 atom combining with 2 atoms of chlorine. So you can also draw a diagram this one to show the nature of bond in calcium chloride. It follows just like the magnesium chloride. You realize that calcium here, atomic number is 20. So when you draw the electronic configuration, you have 282. Then chlorine, atomic number is 17. The configuration is 287. So the 2 of the calcium will have to be given to the chlorine. But 1 chlorine atom cannot take the 2. It can only take 1. And that is why you see these 2 here, meaning that there are 2 chlorine atoms. Each one needs 1 electron from the calcium. So it picks 1. So when you are writing the formula of this calcium chloride and you do not bring this subscript 2, whatever you have written is wrong, because that will mean that the chlorine can take 2 electrons from the calcium, which is not possible. That is why always there are 2 electrons. Okay. Alright, so there are further examples for you to try. They've been solved, but first of all, before you look at the solution, you need to give it a try after you have understood it. Then you compare it to the answers that you have provided, and then be sure of what you have done. If you are not sure of what you have done, then you check it with the answer and then do the right thing. So we have hydrogen sulfide, we have magnesium chloride, we have iron 3 oxide, magnesium oxide, calcium hydroxide. ammonium sulfate and copper 2 tetraoxosulfate 6, that is CuSO4. So they have been solved here. The very first one is hydrogen sulfide. You realize that this is formed between 2 atoms of hydrogen and 1 of sulfur, and then hydrogen is always a positive, so 2 of them, so 2 moles, indicating that we have this 2 there, and then sulfur will gain 2 electrons. So hydrogen 1 added to this, another hydrogen added to this to give us S2 minus, and at the end we have hydrogen sulfide. The next one is magnesium sulfide. Magnesium has atomic number 12, so it gives out the last 2 to become 2 positive, and then the chlorine, 2 atoms of it, each of them will pick 1, and that is why we have magnesium chloride. This is what I was trying to explain in the diagram. The iron 3 oxide, we have iron 3 plus and then oxygen 2 minus. Together they will give us Fe2O3, and then magnesium oxide, Mg2 plus plus oxygen 2 minus, meaning that the magnesium will lose the 2, and then oxygen will accept the 2 to become oxygen 2 minus, and at the end they will form magnesium oxide. So I also explained this magnesium oxide with it, and then the magnesium chloride, so you take note of that. Then calcium hydroxide, calcium 2 plus hydroxyl negative, together forming calcium hydroxide, meaning that the hydroxyl atoms are 2 combining with calcium. You know, calcium atomic number 20, the configuration is 2882, so that 2 will have to be given out. But then OH is minus, in fact it's a radical, and so it can only take 1 electron. So we need 2 sets of the OH in the formation of this calcium hydroxide, and that is why you see the 2 here combining with the calcium to give us the calcium hydroxide. Next one is ammonium sulfate, and in the formation of ammonium sulfate we need ammonium ion and then the sulfate ion combining also to form this. You realize that the sulfate ion is 2 minus. It means that it will need 2 electrons from the ammonium. One ammonium molecule has just this positive, so we need 2 of them, and that is why there are 2 here, so that each will donate a positive to the SO4 to make it SO4 2 minus to balance it. So that is how it is formed. Copper 2 tetraoxosulfate 6, that is CuSO4, like I said. You need copper 2 plus and then SO4 2 minus to form this. So briefly, these are the solutions to the work that we've provided for you. First try it out and then compare your answers to the ones that we have.